So we are on chapter 3, Block Ciphers and DES. DES is Data Encryption Standard. So we will talk about general principles of design of block ciphers, then we go into detail of DES, and then we talk about how to break these codes and how does DES do with respect to those differential and linear cryptanalysis, and then we have general design principles for these ciphers. So first of all, block. What is a block cipher? Block cipher is one which takes a message and breaks into fixed size blocks. Those could be 64-bit, could be 512-bit, 1000-bit, and stream ciphers don't do that. Stream ciphers simply take the bit or a byte and then encrypt it and send it off. Byte comes in, encrypts it and send it off. So it's like a stream, river continuously flowing. Whereas block ciphers are more like post office, where you get a box goes out. You get a truck and a box goes out, and lots of boxes go out. So block ciphers. So a stream is 1 bit at a time or 1 byte at a time, and this is basically a fixed size of block every time. Shannon, who has given us a lot, and you must have heard his name before, the professor at MIT, has also given us in the area of cryptography quite a bit, and he was the first one. In fact, I was reading something. He was the person who originated the whole algebra, field of algebra, which was his master's thesis. So, with that he started, and now he has given us so much. So anyway, so he was the first one, and he says that any encryption we do, it should have two features. First, it should have a diffusion, and second thing, it should have a confusion. Diffusion means if I change 1 bit here, most of the bits here change on the output. If I change 1 bit in the input, most of the bits in the output should change. So remember this kind of a spread. The bits are spread all over. That is why it's called diffusion. Alright. Second thing is confusion, that the relationship should be such that you cannot really figure out what is the input and output kind of thing. So the relation should be very complex. Okay. And so the first thing, for the diffusion, you need to do substitution. And we talked about substitution before. Remember when you substitute B for A in the last class? Well, that substitution was kind of not very good because there was not much diffusion. If you change a bit, it will change a bit probably in the output. Right? So it didn't really diffuse that much. So now in the latest work that we are going to study today, there is a lot of diffusion. When you change 1 bit, half of the bits change. And so that is S box, is substitution. Second thing is permutation. We also learned that last time, permutation, rail fence and things like that, where you change the bytes, change the characters in different places. Well, today we will learn even more complex permutation, where the bits will be moved around so that things look very complex. And you do this basically a product manner. Remember we talked about product means you do one and then you do the second one, both. So we'll do substitution and we'll do permutation. And not only that, we will do that many times. So we call it one round. When we do one substitution and one permutation, that is one round. And then we will do many rounds. So it becomes really complex so that people cannot break it. Remember, this is war. Whatever we are doing, Germany is trying to decode it, or Japan is trying to decode it, and so on and so forth. So we really need to be complex enough so that we are not beaten. And in fact, the whole result of World War II was decided by cryptography. Right? We could encrypt their messages, but they could not encrypt our messages. So this is very important to. So it's very important that this be strong. All right. So Shannon actually did not really tell us how to do these things, but he had the idea. he said that we need to do confusion, we need to do diffusion, we need to have substitution, we need to have all this permutation, but he really did not give a practical method. Somebody at MIT, somebody at IBM called Feistel came up with a method 20 years later, I think, than Shannon, saying that here is a way to do these things, where he said what we need to do is we take a message, break into two parts. The right part, we take the right part and we take the key, combine that in some complex manner, and then exclusive OR with the left part and make it the right part. All right, and we just put the right part on the left, and then we just do on that part same thing. So we take the right part and the key, and take a function, and then we multiply. So this is called Feistel structure. Now it has some good properties. In particular, the decryption is symmetrical, so you can use the same logic as you are using for encryption for decryption. You will see in a minute. So basically, when you get the encrypted message, here it actually starts on the bottom. Basically, when you get the encrypted message, you can take the right part and do something with the last key, and then you keep going backwards in the keys. So you start with K1 through K16. There are 16 rounds as shown here. They don't have to be 16, but 16 rounds are shown here. So the idea is that this structure was so powerful that it has stayed till today. It was done in 70s, and all the block ciphers that we will study in this class, they use this structure. DES that we are going to study today uses this structure. In fact, the ES was designed by Feistel, so obviously it uses that. But the structure is simply, when somebody says what is the Feistel structure, it is simply that break the message into two parts and work on the left half using the right half and the key. All right. So now we are going to apply this to DES or dash, and there are several variables in this structure that can be changed or selected to make it stronger or weaker. First is the block size. You can take 64-bit, or you can take 128-bit, or you can take 512 bits. Second is the key size. You can take 32-bit, 8-bit, 64-bit, 100 or 1024-bit, or 4024 bits, and so on and so forth, 96 bits, and so on and so forth, right? Key size. Number of rounds. We saw there are 16 rounds. You can have 32 rounds, 48 rounds. Subkey generation algorithm. So here we need 16 keys. Those are called subkeys, but you just get one key somewhere. From that one key, you have to get 16 keys. How do you get 16 keys out of one key? Right? That is subkey generation algorithm. Round function. This function here, which is a complex function, which takes the key and the right part, is called round function. This function has to be selected. And then the fast software encryption decryption. Now the second thing is, actually this is just a feature, is that depending upon these, actually that round function, you may be able to do it in software fast or not. Actually when DES was designed, it was not designed for software, it was designed for hardware. And it's very easy to do it in hardware. In software, it requires bit manipulation, which is kind of not very easy. But in hardware, it's very easy to do bit manipulation. If you want to change the bit from, let's say you want to move the third bit to fifth position, it's very easy to do in hardware. But in software, it requires some instructions, which are not that easy. And the ease of analysis. And then you want to make sure that you can prove that it is strong, and that it is still so strong that nobody else can break it. And that's a challenge. And thanks to Feistel, actually his things have stood the test of time. Even after 20, 30 years, things are still working. All right, so let's see DES, Data Encryption Standard. It was published by NBS, which is now called NIST, and we talked about NIST last time, National Institute of Standards and Measurements, I think, something like that. And this is the National Bureau of Standards, and this is in 1977. So you can see about 38 years ago. No, 23 plus 11, 34 years ago. A variation of, so basically the way these standards are done is that they ask for people for proposals, and everyone proposes their own algorithm for standardization so that they can make, they could be ahead in the game. IBM suggested their algorithm, Lucifer, which was developed by Horst Feistel himself, and that was selected. Actually, there were lots of others that were not selected, and this algorithm is a standard for commercial and unclassified government applications. So if you are a bank or something, you have to use this DES for encryption if you want to encrypt things. And for the government, only unclassified. Now you remember, in the government there are two kinds of documents: classified, which are secret, and unclassified, which are public. Right? So unclassified documents can be encrypted using this. For classified, they use much stronger methods. And the key actually was 64-bit, but 1 bit is used as parity, so that leaves 56 bits. Everybody understands what's the parity bit. So when you have 8 bits, the last bit is always set to 0 or 1 depending upon the first 7 bits to make the whole thing even number of ones or odd number of ones. Right? So there are 8 bits in a byte, but only 7 are used, so you get 56 bit independently. It was designed for hardware implementation, and it is used in most financial transactions. So all the banks, etc., use it. Now, since the power goes up by 1 every 2 years, 1 bit, 56 bit was secured in 1977, 34 years ago. Now 17 bits. I mean, it's very easy to. I mean, it's actually possible to break this computationally. So what we do now is we use triple DES. Triple DES means we take DES, encrypt it, encrypt the message, then take the encrypted message, encrypt it again, then take the encrypted message, encrypt it again, 3 times. So instead of 16 rounds, you have now 48 rounds. Instead of 1 key, you have 2 or 3 keys. All right. So anyway, so this is very strong, and is still used, if not as DES, as a triple DES. We have already seen actually most of it, but here is the triple DES. Here is the DES. When you get a 64-bit message or block, you change the bits around first. So there is the initial permutation. Then you do the round 1, get 64-bit, then you do round 2, round 16, and at the end you swap the 2 halves, and then you do the final permutation where you change the bits around again, and you get the final thing. On the key side, you get the 64-bit key, you get 56 out of that by removing the parities, and then you circulate the bits. What is the left circular shift? The last bit becomes the first bit becomes the second bit. Left is going this way. So I mean, depending on how you count the bits, the most significant bit will go to the least significant position. That will be left circular shift. So you do left circular shift, and then you do some permutation on that to get 48 bits, and then basically get 48 bits out of that. And then you do more shifting, and then you do permutation to get 48 bits out of that, so on and so forth. So what we do is, in every round, we take a 64-bit quantity and we use a 48-bit key. Now how it is used? In a Feistel structure, basically, we take the 64-bit, make 232 bits out of that. The right 32-bit is combined with the key by some kind of complex function, and whatever result comes out is exclusive OR the left 32 bits, and then that becomes the basically the right part, and the right part becomes the left part. All right. So let's see a little bit more detail these three things. First is the initial and the final permutation. What is done here? Second thing is the round function. What is done in this plot? And third is subkey generation. How are these keys generated? So the initial permutation is right here. This is specified in the standard, and if you implement it, you get the standards copy, and then you can do that. Basically what it says is that when you get the 64-bit, the first bit goes to the bit 58 goes to the first position, then 50th bit, then 42nd bit, then 34th bit, then 26th bit, 18th bit, and so on and so forth. And this is very carefully set metric. If you change something, it can become weaker. Now it's very difficult for me to explain as to how this is so strong, but basically one of the things you'll notice here is that all the odd bits are here. All the even bits are here. So if you take a 64-bit word, the bits are not next to their neighbors at all. Everybody who was neighboring to you is gone to the next other half. And so that is one way it just sprays them apart, very much. And while you are on the initial permutation, this is the final permutation, which is this at the end here, final permutation. This one says that 40th bit comes first, 8th bit comes here, and so on and so forth. And it is actually inverse of this in some sense, except that I think if you did both, the bits might alternate, or I think that's what will happen. Probably the bits might just alternate. 1 will become 2 and 2 will become 1. Something like that happens. But anyway, so this is final permutation, which is designed to be the reverse of this mostly, except for the bits to get into this one. So anyway, this is very easy to do in the hardware again, but very difficult to do in software, as I said before. All right. So this is the first thing. So you get a 64-bit, and you switch the bits around by this method, so that you get a whole new word, or whole new 64-bit. Then you break into two pieces, 32-bit left and 32-bit right. You take the 32-bit right and make them into 48 bits. And this is where the magic, little bit of magic comes in. Not too much, but little bit of magic. Actually, more magic comes in here. But let's say, so what you do is from 32-bit, you write them down like this. You take bit number 32, bit number 1, 2, 3, 4, 5. Those are the 6 bits. Then you take 4, 5 again, 4, 5, 6, 7, 8, 9. Those are next 6 bits. Then you take 8, 9 again. You take 8, 9, 10, 11, 12, and so on and so forth. So you notice that in every 6 bits, 2 bits are repeated. So 4 bits of the original plus 2 bits repeated. So that's how you make 6 out of 4 are 48 out of 32. Alright, you already have the keys which are 48 bit. Just simply exclusive OR them. That gives you 48 bit. Then you divide them into 8 chunks of 6 bits each. And you take the 6 bits and go through some kind of substitution box which takes the 6 bits and produces 4 bits. And therefore now you get 8 times 4 back to 32 bits. 32 bits, and then you do permutation. Permutation is like this. You take the 16th bit, whatever comes out here, and put that first, 7th bit second, 20th bit third, 21st bit fourth, and so on and so forth. And that's how you get 32 bits. Alright, so there's a lot of things which are not easy to understand. And in some sense, it's difficult to say why did they take 4 and 5 and not, repeat maybe something in the middle or something at the end. And in the beginning, actually, when this was designed, this was all secret. Government knew it, why they are doing this thing, but they didn't want to publish it. Later on, when the other people found out anyway, then government said, yeah, we knew all this, but we didn't want to publish it. Now you know, so we know. So there is a lot of logic behind it which is not well documented, but we will see that this actually does help when we go into the attack scenarios. Again, any questions about this? Is it clear now? The reason is that, please you should understand everything that is happening. If something is not clear, you should know, because one of the homeworks today is to go through the whole sequence one round manually on a piece of paper. So you really have to take the 30-second bit, put the first bit, second bit, third bit, yeah. Okay, I would not use the word hash. I have not used the word hash in this course yet. All right? So we will come to hashes when we come to hashes. So right now, I think you are talking about the permutation function. Is P, E, or the permutation in the previous? So if you keep encrypting it more and more, hopefully it will be harder to break, because here is the thing. One encryption makes it 56-bit encryption. Right? If you encrypt twice, you take another 56-bit key, you have 112-bit encryption. Now somebody has to guess 112 bits before they can break it. Right? They have to get the first 56-bit and the second 56-bit. Right? So it becomes stronger. So there are many permutations here. This one was, you know that this is bit by bit permutation. The 58-bit come here, 58. So this is whole 64 bits are just mingled together, right? All right. Here similar thing is done. There are 32 bits. They are mingled together like this, by this table. So 16th bit comes here, 7th bit comes next, 20th bit comes next, and so on and so forth.
So it's a set. Both of them are set tables.
Oh, these are set tables. These have nothing to do with the keys. So anytime you see a number here on any of these slides, those are fixed. So those are hardware. They are coded in the hardware. When you design a hardware, you know that these bits has to come here and so on and so forth. The keys are not fixed. Right? I won't show you the key here at all, anywhere. The keys are your choice. All right. What is also fixed is this whole procedure, and it is documented so that people can implement it. And these boxes, which I'm going to show you next. Substitution boxes. Those S boxes, they take 6 bits and map to 4 bits. The way they do it is they take the outer bits 1 and 6 to select one of these 4 rows. And then use the middle 4 bits to select the column. Okay? And then the output is given here. So let's say if you had 6 bits. Suppose you had the 6 bits which were 0, 1. Let's say all ones. Let's just be simple, okay? Suppose you had all ones. What would the all ones will be coded? 6 ones, right? What they will be coded as? Bottom row, 1, 1. Because we take the first bit and the last 6th bit, right? And then what column we will take? This column. And the output would be 1, 1, 0, 1. Similarly, if it was all zeros, the output would be 11110. Right? If it was alternating ones and zeros, so 0, starting with 0, 0, 1, 0, 1, 0, 1. What will be the output? So we are going to read the second row, and we are going to read 0, 1, sorry, because we have taken the 0, it will be 1, 0, 1, 0, this one. These are all shift registers, as you know, if you have taken computer science. So you put this value in the shift registers, and the bits are wired so that the output comes out like this. It's all hard coded. So basically, each of these are, shift registers. You are not really shifting anything, but basically the registers, then you put it there. They are resistors. You put the 6 bits in, and then the logic makes 4 bits out. When they come out, then there is another logic here which takes 32 bits and puts out 32 bits by this method. This is just an example. So there are 8 substitution boxes here, S1 through S8. So there are 8 tables like this in the standard. Actually, all these tables are in the book. So for the first, for some particular S box, this is the table, and then you have a second S box which has a different table. You have a third S box which has a different table. Okay, so nothing to do with the key so far. the key comes in, notice that key comes in only here. When the key comes in, it just gets exclusive OR'd. So how do you get the keys? First of all, you start with 64-bit key, which is 8 bytes or 8 octets, and this is the parity bit. You ignore that. If you can see on the screen, this probably is white and this is shaded. Right, so we just take the 7 bits out of each byte and then put them in this order. How do you put it? 57th bit, 49th bit, 41 bit, and so on and so forth. And so we take the 56 bit, but we change the order like this. There are first 28 bits, and this is the next 28 bits. Now, out of 28 bits, we are going to rotate. When we say rotate left and rotate here, when we say left circular shift, that shift is not for the whole 56 bits, but for 28 bits. So this is rotated. Okay? And you take the first 24 bits, so leave the last 4 bit out, and take the first 24 bit. Next time when it is rotated, then you take, then some other 24 bits will come in. Next time it is rotated, some other 24 bits will come in. Now how much you rotate? You rotate by 1 or 2 bits. And that is also specified that in the first round you rotate by 1 bit, second round by 1 bit, third round by 2 bits, by fourth round by 2 bits, and so on and so forth. So you take that number here and rotate by that many bits, take the first 24 bit, and then let's see, yeah, 28 bit, and then permute them. You see, it says permuted choice 2, and this is permuted choice 1. So this permutation is used only in the beginning, and this is used in every round. So this is the first permutation which is used only in the beginning, and this is the permutation which is used in every round. Because of this permutation and because of that shift, you get totally, in some sense, I shouldn't say independent because they're really dependent, but you get some keys that look like independent keys. So the whole thing is about what we call non-linearity. They want to make it complex so that no analysis can really break it. And that's the whole purpose. We'll talk about breaking later on. And everything here was analyzed. For example, why we don't just shift by 1 bit every time. Why sometimes 2 bits, sometimes 1 bit. That makes it nonlinear. And then, so at the time when this was selected, there were other similar algorithms which had different permutations or different S boxes, and they were easily breakable. So now this is where they go into a lot more what we call cryptography than we can go in this course. That is a lot more mathematics, let me put it this way. Okay, but it has been shown that if you change any of these decisions, the only thing you get is a weaker code. Okay, in fact, somebody showed that if you just reduce from 16 rounds to 15 rounds, it becomes bad code. And the way it was tuned was that the IBM actually proposed an algorithm which was broken by NSA, National Security Agency, and then they helped fix it. And they fixed many things. So this is the final standard is not IBM's original proposal. Final standard was something that was fixed by NSA. Okay, and some of these fixes are, for example, NSA helped fix some of these tables. These were, they are, have to be done in a most nonlinear manner you can do. All right, so that's all there is now. I think we have covered the whole DES, which is complex, and actually we managed to do that in so many slides, 4 or 5 slides. The decryption is straightforward. Just like that, for any Feistel structure, the decryption is just, you run the same encryption and you can run it forward in the sense that the whole thing works exactly like this. You could start from here and go down, except that you start with the K16 key, then K15. So you use the last key first, and everything else, this is just a reverse of that. Okay, so you don't even have to go backwards. All you do is you use the keys backwards, the logic works forward. So decryption is straightforward, so now they are going to talk about what is good about this and what is good about any other block cipher. So first is what they call avalanche effect. Basically, I think it's a different name for diffusion. All it means is that one input bit should change at least half of the, or approximately half of the output bits. That is spray, remember? And so this is just another name for diffusion, although the book doesn't say that, but I kind of feel that it is just another name for diffusion. And if you have diffusion, then you cannot guess anything. Remember, in the original substitution that we talked about, where you substitute A to D, there is no diffusion. And therefore, the frequency analysis is straightforward. All you do is analyze the frequencies of the bits, of the bytes in that case, and figure out where the E is. Right? Here, once they are spread all over, there is no frequency analysis possible. And people have analyzed this for DES and found that this is very strong. And you can see this example here. If you take this number, first number, and you go through the 16 rounds, at the end you will get this number, DA02CE, so on and so forth, 32 bits. On the other hand, if you take the second number, which is actually the same as the first number, except that the first bit is different, and you go through the 16 rounds, you get this number. At the end, you see how many bits have changed, and I did that, and I might have done some calculation, but in my head, basically I sat down and did first nibble 3 bits, second nibble 4 bits, and so on and so forth. So there's a difference of 33 bits. How can it 33? Yeah, in 64 bits. So half of the bits have changed just by changing one bit. Now there is one known fact or weakness, if you want to call it, is that if you take bitwise complement of the plain text and use bitwise complement of the key, what you will get is the bitwise complement of the ciphertext. So therefore, you really don't need to analyze 2 raised to 56 keys, because if you have analyzed the complement keys, you can calculate that. So there are only 55 bits that you need to guess. All right? So the strength is 2 raised to 55, not 56. And can you do 2 raised to 56, just brute force the search? And the answer is yes. In 1977, you couldn't do it, but in 1997, people were able to do it on the internet in a few months. What it means on the internet means is that everybody volunteered to give their computing power to this effort. So everybody did piece of the computation, and then within 22 months, within a few months, they were able to find the key by exhaustive search. Right? Few months. Then the next year, and this is all being done by some organization called EFF, Electronic Frontier Foundation, which is a good foundation, but they just want to make sure that we are not using a big encryption. So EFF put a challenge saying that, can we do it any better? Yes, on a single computer, on a dedicated hardware, and actually, I should probably use another word, specially designed hardware. It's not a normal standard computer. That hardware which is designed to basically break DES, they could do it in a few days. And in 1999, the next year, when they combined the two, used the special hardware and at many places, and they could do it in few hours. So obviously DES is a is not that secure, considered as that secure, because some hackers can do this now. Within a few hours they will have the key and they can decrypt things like that. So basically what we use is triple S, but it still is very powerful, like it still is too. So basically there are three kinds of attacks people can do. One is timing attack. In timing attack, you just measure how long is it taking. And some keys take longer and some keys take shorter, particularly if it is done in the software. All right? And if you implement this on smart cards, the cards that have computers in them, and they have to put the key and encrypt and decrypt from your password and things like that. So if the card takes longer, some set of keys are already gone. And so that can be used as a knowledge to reduce from 2 raised to 55 to maybe 2 raised to 45 or something, So that is one kind of attack where you don't have to do all possible keys, but you can do a subset depending upon how long it is taking. So that attack is possible. Although, again, with a smart card, you'll have to sit there for 22 hours before you know the key. Yeah. In hardware, I don't think it makes a difference, because 56-bit has to go there, it has to go there. So that doesn't take. But that is not possible in a smart card and things like that, which have a general purpose processor.